class. Today we're going to be doing section 2.6 from AP Stats, which is introducing you to scatterplots and what to do when you have two variables, x and y. So we're going to start here, and I'm going to do a little bit of calculator work as well using our TI-84 Plus. So basic definition, scatterplots are a type of data display that shows patterns, trends, and relationships between two quantitative variables. So there's the explanatory variable, which is x. It's kind of like your independent variable. And then the response variable y, which is your dependent variable. We don't use independent and dependent mostly because y doesn't necessarily depend on x. There could be other reasons why we see that relationship. We're going to talk about that later. But explanatory and response is a great way to say those. You can kind of think of it like independent and dependent. When describing your scatterplot display, you're going to want to mention three different characteristics. One of them is direction, whether or not your scatterplot is positive or negative direction. So that is more like slope. Strength, whether it's weak, moderate, or strong relationship between the two variables. And form, when we're looking at it, does it look linear? Does it look quadratic? Does it look exponential or logarithmic? I mean, there's a lot of different options. It also is nice to talk about any unusual points or outliers if you see any obvious ones, or subgroups or clusters. If you see like one cluster of points here and another cluster of points here and not much in the middle, definitely want to mention that. So first, let's talk about the correlation between our two variables in the scatterplot. So in our calculator, we use the word the symbol r, or the variable r, for correlation. And this is going to be a linear correlation specifically because we're going to get this r value by running a linear regression in our calculator. So what I've done here is I've taken some examples and I've kind of circled the points, because sometimes, like if we look at this first one here, it almost looks like there's no direction, like it's a zero scatter plot. But if you kind of circle the points here, you can kind of see there's a little slight negative, but it's definitely really weak. I would call this like negative 0.1 or something like that. So pretty weak. This one is just about perfect, negative 1 correlation. So it doesn't get any better than 1, means kind of like 100% correlated. This one is a really good 0 example, this third one. Here we have another negative 1, but this one's fairly strong. It's not perfect. It's still kind of spread out, but I'm going to say that's like a 0.8. And this isn't exact. I'm just going to use this scale below here to kind of guesstimate what it's going to be. Here we have some positive ones. So this is going to be positive, but it's fairly weak. It's really spread out. It's almost, borderline 0. So definitely positive, but I'd say something like 0.2. It's a little stronger than that first example we had. And then this one gets a little bit better, but it's still pretty weak. I'd say something like a positive 0.5. So your values of R are always going to be between negative 1 and positive 1. And you can see this scale at the bottom where I've kind of pieced it together. Now, this isn't an exact science. Statistics has a little bit more wiggle room. But this is my general, how I usually classify the strength of our scatter plot. So anywhere between 0.5 and negative 0.5 is a pretty weak correlation. Between 0.5 and 0.8, positive or negative, that's going to be your moderate section. And 0.8 to 1 on positive or negative is going to be your strong pieces, your strong relationships. All right, so on the next page, we have conditions. So before we can use a correlation, we have a few conditions we need to check, and we really should write them down as well. Variables are quantitative. We need to make sure we don't have categorical variables, that we do have numerical variables. The scatterplot is reasonably linear. Now there's the word reasonably in there because it doesn't have to be perfect, but you want to make sure it's not totally curved, like a quadratic or something. If it is, then we're going to have other ways of kind of straightening that out later in another lesson. And you want to make sure that there's no outliers. Again, in stats, it's a little tricky. If you do have an outlier, it doesn't mean you can't do the problem. It just means that you need to maybe mention that outlier and possibly remove it, maybe not, depending on what it is. Stats is kind of funny that way. Big warning. This is huge. Correlation does not imply causation. it can only show an association between the two variables. So we're going to look at a quick example. It's kind of funny, where just because two things are correlated doesn't mean one causes the other to happen. So example 1, data from a study determined that a strong negative correlation exists between the frequency a 5 or 6-year-old eats snot after picking his or her nose and the number of days that child is sick. Does the data indicate that snot eating after nose picking causes the reduction in the number of days a 5 or 6-year-old gets sick? Explain. So this is where it's really important to remember that correlation does not imply causation. So the data does not indicate that snot eating causes a reduction in sick days because correlation does not imply causation. Now, just stating that sentence isn't quite enough. We want to give an alternate reason as to why we might see that happen. So what could be a confounding or lurking variable that could cause that? So alternate reason behind reduced sick days, and this is just me being creative, is that snot eating, let's see, snot eating, or, I see. I said, I wrote this a little differently. Okay, so another reason why we might see a reduced sick days is because he or she has no friends, which is a little sad, but because he eats a snot, or he or she eats a snot, he or she might not have no friends, which means they are less exposed to germs from other kids. So it might not actually be the physical snot that they're eating that gives them a super awesome immune system. It might just be because the kid doesn't have very many friends because he keeps eating his snot and therefore is less exposed to germs. All right. Example 2, we have freshmen at the Webb schools go on a backpacking trip at the start of each school year. Students are divided into hiking groups of size 8 by selecting names from a hat. Prior to departure, each student's body weight and backpack are measured in pounds. And here are the data from one hiking group. So you're going to want to pause this video and put this data into your calculator. And let me kind of show you here what that looks like. We're going to go to Stat and then Edit. And then I've already put these into the calculator in my L1 for my body weight category and L2 for my backpack weight category. And you also, before we run this linear regression, you want to think about which one is the explanatory and which one's the response variable. It's kind of like, it depends on what your body weight is, how much backpack weight you can hold. So the body weight is going to be our explanatory variable that explains how much we can hold in our backpacks. So this is going to be our X variable and our Y variable here. They won't always put them in the right order, X first and Y second, but a lot of the time they do. All right, and then so you're going to want to put those into your list, and then we can run, well, we can run it right now. So Stat, so to run our linear regression, you're going to go to Stat, you're going to go over to Calc, and then there are two different linear regressions. There's this one, linear regression AX plus B, and there's linear regression A plus BX. It doesn't really matter which one you use. We always use the A plus BX because it's the one our book uses. So I'm going to hit enter. And then, this is for my second set of data. So I'm going to change this to L1 and L2. And then we can, if we need to graph it, we can store our regression equation in our Y variable so that it puts the line on our graph for us. We're going to do that in the next example. All right, so I'm going to calculate. And I have a bunch of information here. So I have A, which is, if you think about a linear equation, this is like my y-intercept. B is my slope because it's attached to X. I have R squared, which is our correlation of, our coefficient of determination, and R, which is our correlation coefficient. So we're not going to talk about R squared yet, but we are going to talk about R. So the correlation coefficient measures the direction and strength of a linear relation between two quantitative variables. So this is a linear regression. So this R value, it automatically applies to linear association between them. And in this example, our R equals 0.795. You want to use at least 3 decimals in AP Stats. And when we want to interpret that R value, this is where we're going to go back to those 3 characteristics we talked about. We have direction, strength, and form. So there exists a positive, I'd say moderately strong. Sorry about my handwriting. That's horrible. Let me write this again. Moderately strong linear relation between the student's body weight and the weight of their backpack among freshmen at web schools. So you always want to include context as well. Right, our next example, we're going to go through and actually construct a scatter plot. So we have, as reported in the Journal of the American Medical Association, for a study of 10 non-agenarians or subjects who were aged 89 to 91. The following tabulation shows a measure of strength, heaviest weight subject could lift using knee extensors, versus a measure of functional mobility, time taken to walk 6 meters. Note that functional mobility is greater with lower walk time. So if you think about how long it takes them to walk that 6 meters, the shorter time is going to be better in mobility because they can do it faster. So we have our strength, we have our walk time. Again, strength is going to be our explanatory. The time it takes them to walk that is going to be our response variable. So explanatory is strength in kilograms, so that weight that they can carry. And our response is going to be walk time in seconds. It's always good to put your units in there. All right, so constructing a scatter plot. So again, you're going to want to pause this video and put these values here into your calculator. So stat, edit, and then I've already populated them into my L3 and L4 lists. You can always replace your L1 and L2 with those lists as well. And then to construct a scatter plot, what we're going to do is first we're going to run our linear regression. So we're going to go to Stat, Calc, and then we're going to go down to 8, linear regression, enter. I'm going to change this to L3 and L4 for my new data. And then here's where I'm going to store that regression equation. I'm going to hit stat, no, I'm not. I'm going to hit vars for variables, go over to yvars, the first one function, and y1. There's a lot of different ways to get this y1, but that's the way I always do it. And then go to calculate, hit enter. It's going to give me the same information as before, but that putting the y1 in there means that when I look at my scatter plot, I'm actually going to see this line. It's giving me a line. I'm going to see the line on my graph. So now I'm going to go to second, y equals into our stat plots. I'm going to, whatever my first plot, I usually leave that first plot available for box plots and histograms and things like that for quantitative variables where I just have one variable. And then I'm going to turn that off. Then I'm going to go back to here and I'm going to go down to plot 2. I'm going to turn this on and I'm going to select the first one, which is the scatter plot. If your data is in L1 and L2, just make sure you have L1 and L2 in here for X and Y. I put mine in L3 and L4. Now I'm going to go to zoom and I'm going to go down to the 9th one, which is zoom stat. And here's my scatter plot. So we've got our points of data, which are these red boxes here. And then this line is that linear regression line of best fit or least squares regression line that we ran. And I told the calculator when I ran the linear regression to put the my equation into y1. So if you look in y equals, you can see that equation in y1. So that's how I'm getting that graph. Now, when we draw our scatter plot, we want to make sure that our axes are labeled. It's super important. We don't actually need them to be scaled. It's nice if it is, but we definitely need them to be labeled. So y is going to be walk time with your units in seconds, and I have strength in kilograms. And then it's easier for me to draw my line if I, let's see, if I hit trace, I can kind of figure out where this is, but I can also look at my equation. So look at the A value in the equation. It's at 44.25, and this Y value, is, it says 40.6. Maybe it's not exactly hitting my X. Oh yeah, see, it says X is 1.5. So I don't exactly see that that x equals 0 y-intercept. But I know that it's going to hit my y-axis at 42, a little bit more than 42. So I'm just going to put that there. And then I'm going to come all the way down to see where it lands when y is 0. Hopefully I can see it, or I can see close enough. There we go. Over to 18 or so, a little past 18. So I have this linear regression line, and then it's easier for me to draw my points around it. So they don't have to be perfect. If you have your trace function on, you can kind of jump around to seeing what these are. It's a little hard to like get them all. They don't have to be perfect. So I just usually kind of eyeball it, do something like this. And I guess if you're eyeballing it, it's probably better not to have it scaled and just have it labeled, which is what I usually do. It's okay in stats. As long as it looks like it's supposed to, it doesn't actually have to be exactly the points. All right, so there's a pretty good picture of my scatter plot. All right, now, what is the sign of the slope and what does it signify? So if I go back, I'm going to go back to my linear regression and just run that again really quick so I have it on my screen. So my slope here is our b value, and that's a -2. You can also tell by your graph that had a negative slope, so the slope is negative. And it says, what does it signify? So now in context, what does that mean? Well, it shows that the non-agenarian's strength, or as the strength increases, their walk time decreases. So it doesn't have to be super fancy. I wrote that makes them go faster, which is good. They get faster. Is the y value, or the value of y, determined solely by the value of x? No. The value of y is not determined solely by the value of x because the correlation does not imply causation. So this is another example of that. Other factors could be overall lifestyle, healthier diets, etc., like that. And then draw your fitted line for the data. So we already did that. We kind of used our calculator to give that to us. And then find the exact equation of the fitted line. So here our A value is 44.256 and our B value is -2.435. So when I write out my equation, I'm going to have 44.256 minus 2.435x. And we already have x and y defined up here. If you did not define them earlier in your problem, you will need to define them here with your equation. Notice I put y hat. Instead of just y equals, I put y hat equals, and it's because y hat is the predicted value of y. Notice on our graph, that line doesn't go through the actual points. So that's not the actual value of y given our x value. Those are the points we got, but it's the predicted value of using our least squared regression line. All right, and that's it for today's lesson.